Can you see my screen now? Hello? Hello?
Yeah, hi, I'm able to say.
Fine, all right.
I wasn't, yeah, sorry.
Okay, okay, fine. Then we are going to discuss about multi-threading and what
Okay.
threads are, the life cycle of threads. So let me check whether I have supporting image or not.
Ahmed, I have one general question.
Yes?
Probably like, are you in recording now?
Yeah, yeah, I'm recording. Do you want me to pause?
Can you pause?
Okay, so we are looking into multi-threading. In Java. So before that, let us see what process, job, task is. So the thing is, uh, process, job or task means the same. That is performing an activity. Activity may be downloading a file on your computer, listening to music file, or executing a program, composing a program. All these are activities. So each activity can be treated as a process or a job or a task. And these jobs are actually executed by CPU. Particularly, the processor is going to process a process, that is process a job. So here the processor is going to process the process. Here the process here is noun, and here this process is verb actually. And this process is also nothing but job. So the processor is going to execute a process. And in computer, we have environment like a multitasking environment, single tasking environment. So let me tell you what single tasking environment is. So here, assume I have a CPU here. So this is the CPU. So, this is CPU. Let me name it here. Ah, that is nothing but processor. So to this processor, I am going to assign tasks. So the tasks are traveling in a straight line. Assume this straight line is the path through which the processors are moving towards the CPU. So here, assume I have four processors. Three, yes. So let me name them P1. So for example, P1 is downloading a document. Downloading a document. And let's say it is taking 1 minute to download. And P2 is listening to a music file, that is Assume it may take 3/4 minute to finish listening to a music, and here executing a Java program. Half minute, and here composing the biodata in a Word file, and assume it takes 1 minute. So it means process P1 is given to CPU, and the CPU, if it is continuously working for 1 minute, then downloading the document gets finished. So I mentioned the time also that is required by each process, so that CPU will be finishing that by that time. So here all these processes are moving through this black line. So here in single tasking environment, so what happens is each process is executed once. So P1 process is given to CPU, and the CPU is continuously executing on P1 process for 1 minute. It means for that 1 minute, P2, P3, P4 that are in queue should wait for the turn. So here P3, I think I missed to enable P3, P3, P4. So the other processors should wait in the queue. Once 1 minute is finished, the P1 process gets finished and P2 is given to CPU. So it means at a point of time, CPU is going to process only single process, and the other processes should be waiting in the queue. So in that case, the last process P4 to get finished, it has to wait for 1 minute, then 3/4 minute plus 3/4 minute plus half minute. So the total time it has to wait, and only then P4 process would get it done to with CPU, and CPU then starts executing it. So this is what happens with the single tasking environment. Our operating systems, Windows, Mac, whichever we are using currently, are multitasking environments. It means multiple tasks can be executed at a time. So I am explaining you how this multitasking goes in operating systems. So multitasking environment. So what happens is I have the CPU here. So let me label it here, CPU. And here I have processes in process queue. So I am going to draw the process queue here. Yes. And I'm going to mention the processes here. So let me label them P1, P2, P3, P4, P1, P2, P3, P4. So the same process I am mentioning here, and they are given to CPU in this path. So this is the job queue, and here they go to the CPU like this. And here P1, P2, P3, P4. So here this is a job queue. Let me mention the name here. Job queue is a process queue, job queue. Process or job queue. So P1 is given to CPU, and of course P1 requires 1 minute for processing. So the thing is, assume here, I am going to mention here CPU can spend 1 minute for processing, assume. And there are totally 4 tasks currently that are running. So there are 4 tasks running currently in the job queue. So if that 1 minute is divided among those 4 tasks, then CPU can spend, so 1 minute, that is 60 seconds. 60 seconds by, there are 4 tasks currently available, so CPU can spend 15 seconds on each process for execution. So this 15 seconds is known as quantum, we say. Quantum. This is physics related thing. Okay, quantum. Now 15 seconds is being spent by CPU on each process. I am going to mention here the timeline. So timeline and the remaining time available for each process after process. So I'm going to write here tasks are say processes, and then let me put here P1, P2, P3, P4. So I just labeled all the 4 processes, and I say execution round. So for the first time, these processes that are available are given to processor to process. So P1 will be given to CPU here. P1 will be given. Now P1 gets its turn. Now if you see here, P1 will execute for 15 seconds, and the remaining 3/4 minute it needs to be processed. I mean to say, I am mentioning over there the remaining time, 3/4. Better say, I say 3/4. And for P2, it is something like P2 is 3/4 minute it is taking, and after processing for 15 seconds, it needs half minute. P3, it is half minute and it requires another 1/4 minute. And P4, it requires 1 minute, and so after processing it gets 3/4 minute. If you see over there, I mentioned the remaining time here. So for the first time, so what happens is here in my picture, P1 is given to CPU. Now CPU process for 15 seconds and it generates partial results. So let me store the partial results here. Yes. So it stores partial results here. I am mentioning here partial results. Now the P1 after 15 seconds generates the partial results here, and from here again it goes and joins this queue. That's what happens for all the process. Then P2 is given to CPU and CPU is given for 15 seconds. Then it stored the partial results here and again it is sent back to the queue. So like this, for first time, every process in the job queue will get its turn 15 seconds and get executed by CPU and they join the process queue back. So here for second time that is round two, they again go to CPU. So CPU has already executed partially and the partial results are consumed. So after consuming the partial results, then the other 15 seconds by CPU is spent on second time on the same process. So I say here round two. I mention here. Round two. So the remaining time is half minute, and here the remaining time is 1/4 minute, and here of course it gets finished. I mention it as finished because the remaining 1/4 minute 15 seconds. So CPU after spending this gets finished. Then half minute. Then round three. So round three. So round three. 1/4 minute is remained now, and this gets finished, and this we already don't have. So what happens is process P3 is removed from the job queue. So this is removed from the job queue. This should be removed from the job queue. Then only 3 processes would be. And here I go back here. Let me finish that. So this is not available and this requires another 1/4 minute. Then next round. So next round, if you see by round four, this gets finished, and of course this also gets finished. It means 4 rounds it need to execute all the 4 processes that are available. So this kind of a scheduling the processes to CPU for processing is known as round robin scheduling, we say. So round robin scheduling. And this is an algorithm Maybe you might have seen this somewhere in your academics. So the operating system uses various algorithms to process the jobs that are available. And here the thing is, at a particular point of time, CPU has only one process with it. Whereas it is multitasking environment. So here, after 15 seconds, immediately the second process goes from the job queue to CPU. It means the one process is switching by other one. So here, this switching time is very minute in our operating system, and we humans are unable to notice that. So it is maybe thousandth, a millionth part of the second. So where we humans are unable to notice that switching time, and for us it looks like multiple tasks are executed simultaneously. Actually, at one particular point of time, only one process is getting executed, and it is being switched by other process after the quantum time, that is 15 seconds in my sample gets finished. This is an example for multitasking environment. So here, with this, we had an introduction to process, then single tasking environment, multitasking environment. Then how about threads? So here, let me write here. Save this. Let me go new one. So I write here threads. Thread is actually a part of the process which has its own execution path. Which has its own execution. Let me explain you what this own execution path is. For example, process P1. So let me write process P1 process, and let me give color to this. So this process, let me write in, assume this is process. So this process is given to CPU. Now this process, what I am doing is I am going to divide that process into multiple threads. So here I say this is one thread, another thread, another thread. I name it as T1 thread 1, T2 thread 2, T3 thread 3. So, and here is my CPU. So I assume this as CPU, and I name it here CPU. And what happens is every process is going to be given to CPU in its own path. You can see thread 3 is given to CPU in its own path. This like this like this. If you see, every thread is going to CPU in their own path. So we can assume CPU like having multiple hands. So each hand performing one task. So more number of threads, more amount of work can be done. That is more number of hands given to CPU and more amount of work can be done. And here, let me give you an example. why these threads execution is higher, I mean faster than process execution. So let me write here, process are actually lightweight components, heavyweight components, heavyweight components. It means they consume more computer resources, that is CPU time, memory. So they consume more computer resources, more memory, more CPU time. Whereas threads are lightweight components. So lightweight components in contrast to heavyweight components will consume less computer resources. So they consume less computer resources and they are faster in performance compared to heavyweight components. Yes. So let me explain you by scenario. I'll write the scenario here. I have payroll processing and I have one process here. So payroll processing and I have one process. This is executing 1,000 employees. So 1,000 employees payroll. So for payroll, the salary is being computed for the employees for that month, consuming the number of leaves he have availed and the number of leaves available, then how many hours he has worked. So his traveling, dearness allowance, deducting the PF, all those things are considered and payroll is, I mean salary is being processed. So assume to process one employee salary, it is taking 1 second. 1 second. It means 1,000 employees will be consuming 1,000 seconds to process. It means my process, one process is consuming 1,000 seconds to process the payroll for 1,000 employees. Now what I am doing is, I am going to divide this process into threads, three threads. So process is divided into three threads. So the thing is, we can break down a single process into multiple pieces and each piece is termed as a thread here. So thread T1. So T1, what I am doing is for T1 I am assigning 400 employees. T2 I am assigning 300 employees. And T3 I am assigning another 300 employees. It means my first thread will process 400 employees and the second thread will process 300 employees. Third thread will process 300 employees. So totally 1,000 employees are being processed with three threads. So here, of course, to process 400 employees, how many seconds it takes? 400 seconds. And to process 300 employees, obviously it takes 300 seconds. And another 300 seconds. So the thing is, what happens is, here So let me draw a simple graph here. And here, red line. Yes, look here. I will represent the timeline here. Timeline. And here, processes. I mean threads. Threads. So I'll mention the timeline something like till here 100, till here 200, till here 300, and here 400. I mean 100 seconds, 200 seconds, 300 seconds, 400 seconds. So here if you see my thread T1, so how many seconds it takes? 400 seconds, right? So till 400 seconds here, this 400 seconds. And T2 takes 300 seconds. 300 this. T3 takes 300. If you observe over there, all these threads are parallelly processed because every thread has its own execution path. So all these three threads are parallelly processed, and of course in 300 seconds these two gets finished. These two gets finished. So these two get. And by the time 400 seconds get finished, by the time here, all the threads, I mean to say all the employees payroll process is being finished. It means totally how many seconds it is consuming? In 400 seconds, all the employees payroll process is being finished. So it means threads, while they are parallelly working, they are able to give higher performance when compared to process. So this is how threads are higher in performance compared to the process, which are heavyweight components. So I believe you are able to understand this example of threads that give higher performance, right?
Yeah.
Fine. Let me save this. Okay. For now, I'll wind up the session because I'm late, and we'll continue tomorrow. I'll execute a sample using threads, and I'll introduce thread lifecycle, then methods present in the thread. I mean, they are classes actually in our Java, and methods
Okay.
present in it, how to name a thread, and are there any currently running threads in our JVM? Yes, of course we have, and we will be talking some more about threads, and we'll be executing samples hopefully tomorrow. Tomorrow session we can put a full stop to threads by examples.
Okay.
Okay.
Sure. Yeah. Thank you very much.
All right. See you tomorrow.
Yeah. Sure. Bye.
Okay. Bye.